All right, welcome everybody. We're going to go ahead and finish up our chapter 7 unit by talking about a little bit more graphing of rational functions. We're going to kind of combine some of the topics we've already talked about, vertical asymptotes and horizontal asymptotes, with some of the algebra that we've been doing, the factoring and the simplifying and the restrictions, and then we're going to see how does each of those different components relate to the graph. We're going to keep this relatively simple. We're not actually asking you to create the graphs from scratch. We're asking you to understand how the algebra relates to them and how you follow the rules to find each individual piece. So here we have 6 steps, and we're going to go ahead and do them one at a time for each problem to make sure that you understand what's what. So here in step 1, we are going to find what is called a hole for short, and then the fancy way of saying it is a removable discontinuity. In order to find any holes, you're going to first factor the numerator and denominator. That's what we've been doing for the last several lessons. You're going to simplify if possible, which means cancel out any common factors. If anything cancels, then there is a hole there. And please note that if you have more than one canceled factor, you are allowed to have more than one hole. Although, again, for now, we're just going to stick to one at a time. And then if there is a hole, you have to tell me where it is. It has to be an ordered pair x comma y, and you're going to go ahead and find that x comma y by substituting whatever the restricted x value is into the simplified form. So let's take a look here at number 1 and point out a couple of different things. So when we talk about a hole, we are talking about a literal hole in the graph, usually denoted with an open circle. Please note that on graphing utilities, Desmos or the graphing calculator, you will not be able to actually see the hole. So you have to know that it's there. And again, we're going to draw it as a literal open circle. The reason why the hole exists, and again, that is the point 3 comma 2, so we can see it on the graph, but what we want to do today is make sure we understand algebraically why it happens. So if we go back to the steps for the hole, first step is we're going to go ahead and factor the numerator and denominator, which you can see I did for you. Factors of positive 3 that add up to be negative 4, and factors of positive 6 that add up to be negative 5. Just like always, you are allowed to cancel the x minus 3's from the top and the bottom. When you do that, you now have what's called the simplified version, which means that for all the steps going forward, you're going to go ahead and use that simplified version. In order to actually find the hole, you have to find the ordered pair x comma y, and here's how you do so. Whatever factor you canceled out, which in this case was x minus 3, you would set it equal to 0. Whatever that value of x would be is the x coordinate of your hole. So we would know that it's at 3 comma something. In order to actually find that something, you would plug the 3 in for all the x's in the reduced form. So 3 minus 1 over 3 minus 2. 3 minus 1 is 2. 3 minus 2 is 1, which is how you know that there is a removable discontinuity, or a hole for short, here at the point 3 comma 2. And again, we have graphed it for you. We're just trying to make sure you understand how the two things are related. Then vertical asymptotes, we've talked about these before. You're going to go ahead and use the simplified equation, and you're going to set anything in the denominator equal to 0 and then solve. So using the simplified version, the only thing in the denominator is the x minus 2, which we would set equal to 0. Solve for x equals. And then again, when you're talking about a vertical asymptote, you are talking about a line. So the vertical asymptote x equals 2 is here, which again, you can either draw with a highlighter or with a dotted line. Gets a little more complicated for horizontal asymptotes. There are 2 rules that we're going to use. We've seen one of them formally. The other one we've kind of only seen informally. So here for these horizontal asymptotes, we are going to do either one of the 2 cases. You have to compare the degree of the denominator with the degree of the numerator. If they happen to be equal, then your y equals the ratio of the leading coefficients. We've already seen that. Then the one we've only seen informally is if the degree of the denominator is greater than the numerator, then there's going to be an asymptote at y equals 0. So we kind of did that in terms of transformations, but it still is the case. So again, we're going to use the simplified equation. So we're going to look at x minus 1 divided by x minus 2. If you look at the degree, you can see that these are both x to the first. So if you wanted to find the horizontal asymptote, you have 1 over x minus 1, and then 1 over x 1x minus 1 over 1x minus 2. In order to find the horizontal asymptote, you are going to find the ratio of the coefficients. So, of course, 1 over 1 turns out to be 1. That means that that is where your horizontal asymptote is. And again, you can either draw it with a color or with a dotted line. So then there is something called a slant asymptote. And again, these are all abbreviations. So when it comes to a slant asymptote, this only occurs in one particular case. It only occurs if there is no horizontal asymptote and the degree of the numerator is exactly 1 degree larger than the degree of the denominator. It didn't happen in this one, but it will happen later. If that happens, you're going to use your old friend long division. You're going to ignore the remainder, and then you're going to write the answer as y equals mx plus b. Again, the only way that can happen would be if the degree of the top was larger than the degree of the bottom, which we already know is not the case. So we're going to go ahead and just say none. There are no slant asymptotes. Then x-intercepts and y-intercepts, obviously we have found those lots and lots of times, although maybe not lately. So when it comes to an x-intercept, normally you set y equals 0 or f of x equals 0, and you solve for x. As a little bit of a shortcut, you can just set the factors of the numerator equal to 0 and then solve for x. Again, you have to use the simplified version. So if your simplified version is x minus 1 over x minus 2, in order to find the x-intercept, you're going to set the factors of the numerator equal to 0. You're going to solve. An x-intercept should be an ordered pair. So in this case, 1, 0. And again, if you compare that to the graph, 1, 0 looks correct. And last but not least, we're going to go ahead and talk about the y-intercept, which is the easiest one. Set x equal to 0 and solve. Again, use the simplified version. So if you go ahead and find the y-intercept, you're going to get 0, something. If you look at the simplified version, you're going to get 0 minus 1 over 0 minus 2. That's going to give you a negative 1 divided by a negative 2, also known as a 1/2. And hopefully you would agree that positive 1/2 as your y-intercept looks to make sense. So again, we're not going to ask you to create that graph yet with all of those components. That's more of a pre-calc thing. But we're just trying to make sure that you understand how the pieces are related. So let's go ahead and try number 2. Again, you can always refer back to that list of notes as needed. So here in number 2, notice there was very little factoring to do. All I did was simply factor the 2 out of the numerator, and that gives me my simplified version here. Remember, going back to step 1, there would only be a hole if there was a cancellation from the top and bottom. Because there is no cancellation, there are no holes, which is perfectly fine. To find a vertical asymptote, you set the bottom equal to 0, solve, and that's going to give you a line. So again, x equals negative 2. That is going to be my vertical asymptote. To find the horizontal asymptote, you're going to look at the degrees, and you have to be just a little bit careful here. So even though you factored this 2 out, you have to assume that you have to remember what it was like when it still was there. So when it still was there, you would have a 2 in front of the x on top versus a 1 in front of the x on the bottom. So you are still going to use that idea of coefficients because it's the same degree, which means you're going to get a horizontal asymptote of positive 2. And again, we want to make sure that that checks out, which it does. Slant asymptotes can only occur if the degree of the top is 1 more than the bottom, which again does not happen yet. To find an x-intercept, you would set factors of the top equal to 0. If you set the entire top equal to 0, hopefully you would agree that the 2 cancels out because you could just divide it away, and all you would get would be x equals 1. Remember that an x-intercept is an ordered pair, so 1, 0 hits the graph between 0 and 2. Finally, for the y-intercept, remember it has to be 0, something. You're going to put a 0 in for all of the x's. So if you do that, you would get 2 times 0 minus 1 over 0 plus 2. That's going to give you 2 times negative 1, which is negative 2, divided by 2, which gives you negative 1. And hopefully that is where the graph appears to cross the y-axis, which I would hope that you agree that it does. So a few more here just to show you the relationships, and again, getting slightly more difficult as we go through. So here in number 3, again, step 1, you are going to factor. So factor the top, then factor the bottom. Remember, that's the difference of squares. Notice you have a double x plus 1, so those are going to cancel. And then here is your simplified version. Everything that you do from this point forward should be done to the simplified version. The whole should present itself immediately. You take whatever the canceled factor was, in this case, x plus 1, set it equal to 0, and then solve for x. The whole has to be an ordered pair, so -1 comma something. In order to find the something, you're going to take that -1 and you're going to plug it in for all the x's in the simplified version. So -1 minus 3 is -4. -1 minus 1 is -2. A negative divided by a negative is a positive, and in this case 2. And hopefully if you take a look at -1 comma 2, that's exactly where my nice big open circle or hole is. To find the vertical asymptote, you're going to set anything from the denominator that didn't cancel. So if you go ahead and set x minus 1, you're going to get x equals +1. And again, that is your vertical asymptote. Got a little bit nicer for you. The horizontal asymptote, again, looking at your simplified version. All you really care about is 1x over 1x, which means if you, again, look at the coefficients, 1 over 1, you're going to get a horizontal asymptote of 1, and that tracks. Slant asymptote, again, does not happen unless the degree of the top is exactly 1 more than the bottom. We'll see that in our final example. X-intercept, you're going to set the numerator of the simplified version, solve for x, and make it an ordered pair. So 3 comma 0. And again, 3 comma 0. Hopefully that's where the graph crosses. And then finally, the y-intercept, 0 comma something. You're going to put a 0 in for all the x's. So 0 minus 3 over 0 minus 1 gives you a +3. And would you look at that? I think it's safe to say that that is, in fact, the y-intercept. So again, when we ask you to do some practice problems or some homework problems, we're really only asking you to do exactly what we've done here. Could you follow the steps that were laid out, find the algebraic answers on the left, and then make sure they match up with the graphs on the right? So in our final example here, you can clearly see that there is a slant asymptote. It's the diagonal line that's dotted. So I'm going to make sure you understand how to find it. Again, you're still going to follow all the steps in order. So number 1, factor anything you can. So factor the top as the difference of squares. Notice that there are no cancellations. So if there are no cancellations, there are no holes. To find a vertical asymptote, you would set the denominator equal to 0. So x plus 2 equals 0. And if you solve for -2, remember that is your vertical asymptote, which goes up and down. When it comes to the horizontal asymptote, so if you take a look at these two versions, this version over here on the right is not considered to be simplified because you didn't cancel anything. All you did was factor it. So if you're trying to find the horizontal asymptote, it actually is easier to look at the degrees on the left side, because if you were going to do it on the right side, you'd have to add those x's up. What you're seeing here is that the degree on top, 2, is bigger than the degree on the bottom, which is 1. And if that's the case, there is no horizontal asymptote, but there is a slant asymptote. So again, if you go back to the rules on the front page, a slant asymptote occurs if the degree of the top is exactly 1 more than the degree of the bottom. How do you find that slant asymptote? Well, you have to use our old friend long division. So when you go to do long division, you're going to put your denominator outside. That's the divisor. Then you're going to do x squared. You're going to do a 0x minus 9. And just as a reminder, that 0x is a placeholder. Hopefully it hasn't been so long, but when you're doing long division, you're always trying to do first into first. So basically, how many times does x go into x squared? Or a better way of saying that is x times what is x squared? And that would be x. Then you have to take that x and multiply it to both things in your divisor. So x times x is x squared. X times 2 is 2x. Then you have to subtract. You may or may not remember when you draw the line, you change the signs. So the squareds are gone. 0 minus 2x is negative 2x. And then you're going to bring down the negative 9. You're going to go as many times or as allowed, and you are allowed to go again because you're putting an x into an x. So again, you're always doing first into first. So basically, x times what is negative 2x, and that would be a negative 2. You're going to multiply that negative 2 to both values of the divisor, giving you negative 2x minus 4. When you draw the line, you change the signs. The x's cancel, and you're left with a negative 5. You can't go any farther because x doesn't go into negative 5. Again, if you refer back to the previous page, after you perform the long division, the rule says you're going to ignore the remainder, and you're going to take whatever you got as your quotient. You're going to write it as y equals mx plus b, and then you're going to graph it. So how do you graph y equals x minus 2? Well, you start at the y-intercept, which is negative 2. Then you go up 1, right 1, up 1, right 1, up 1, right 1, and then down 1, left 1 as many times as possible. And that's how I wind up with my slant asymptote. To find my x-intercepts, I am going to set my my numerators equal to 0, and notice that there are 2 of them. There's an x minus 3, which gives me 3. Then there's an x plus 3, which gives me negative 3. So for the first time today, we have 2 x-intercepts, and yeah, that's perfectly legal. Finally, you're going to go ahead and find the y-intercept, which remember is 0 comma something. In order to find the something, you're going to put a 0 in for all the x's. You can use either version because, again, the right side is not more simplified. It's just more factored. So if you use the right side, you're going to get a negative 3 times a positive 3 over a 2. That's going to give you a negative 9 over 2, better known as negative 4.5. And if you look at 0, negative 4.5, I think you would agree that that is perfectly reasonable. So if you go back to the rules on the front page and you try to apply them to any example that we give you, hopefully everything should match up perfectly. So thanks very much for tuning in, guys, and we will catch you next time.